The open ocean is a world without walls, no coral ledges to spring from, no underwater canopies to crouch beneath. Here, in the endless blue, there is nothing but space and speed. Prey cannot vanish into reef cracks. Predators cannot lurk in shadow. Every encounter is visible, every movement magnified, every second decisive. This is a battlefield stripped of cover, where evolution demands a single defining trait, the ability to move faster than anything else alive. Below the surface, a quiet war is waged in pure physics. Water, though it appears fluid and forgiving, is an unforgiving medium for motion. It resists, it drags, it clings to skin, scales, and fins with the weight of invisible hands. For any creature that wants to hunt here, truly hunt, not scavenge or stumble upon a meal, that drag must be conquered. Evolution doesn't grant wings to ocean predators. It grants streamlining, efficiency, and relentless refinement in body design. In the ocean, speed is not about choice, it's about survival. Take the mako shark. Sleek, bullet-shaped, with a narrow snout and conical body, the mako is a masterclass in hydrodynamics. Its skin is cloaked in denticles, microscopic backward-facing scales that reduce turbulence and slice through water like the texture of a jet wing. When it moves, it doesn't simply swim, it accelerates. With a crescent-shaped tail and high aspect ratio fins, long and narrow like the wings of a falcon, it converts raw muscle power into efficient forward thrust. This design isn't random. It's the result of millions of years of evolutionary trial and error, a process where every shape not built for velocity was trimmed from the gene pool. But speed isn't merely the product of outer form. Internally, these animals are just as specialized. Unlike most sharks, makos maintain partial endothermy, a form of regional warm-bloodedness. By heating key areas of their body, like their swimming muscles, brain, and eyes, they sharpen their reflexes and sustain bursts of energy at speeds few other fish can match. It's an evolutionary edge borrowed from birds and mammals, and it turns the mako into a predator with both physical and neurological speed. Yet the mako is not alone in this arms race. Enter the swordfish, a torpedo with a blade. Its body is a sleek, torpedo-like capsule, free of excess. Its long bill not just a weapon, but a hydrodynamic aid, slicing through water and reducing resistance. It also heats its brain and eyes, not for warmth, but for clarity and speed of perception. In the murk of the deep or the blur of a chase, it sees faster and reacts quicker. A split-second edge that means the difference between striking a mackerel in full flight or missing it entirely. Swordfish, like their cousins the marlins and sailfish, have evolved a body plan that minimizes drag to near perfection. Their scales are small and embedded, their bodies rigid and tapered, their dorsal fins capable of tucking into grooves to reduce water resistance mid-chase. Even their pectoral fins can be locked against the body, aerodynamic design transferred to aquatic life. Every anatomical detail serves a singular purpose, to maintain speed at maximum efficiency. But speed has its costs. For these predators, a missed strike doesn't just mean hunger, it means wasted energy, oxygen, and exposure. Unlike reef ambush hunters or deep-sea ambushers, torpedo predators have to power their movement constantly. They cannot pause. They cannot drift. Many are obligate ram ventilators, meaning they must swim to breathe, forcing water over their gills. Speed is life support. Rest in many cases equals suffocation. In the open ocean, where schools of prey like mackerel, sardines, and flying fish have evolved their own countermeasures, shimmering camouflage, high-speed escape, chaotic directional bursts, the pressure to move faster and strike cleaner becomes relentless. Predators that once relied on brute force or opportunism were outpaced and outcompeted. Only those that could match prey velocity, anticipate turns, and outmaneuver the collective intelligence of a school survived. Over time, nature favored bodies shaped less like fish and more like weapons of pursuit. Hydrodynamic efficiency defines this biological evolution. The ideal ratio of body length to width, the ideal positioning of fins for lift and control, the internal muscle mass allocation for sudden bursts, all of it is tuned by the same principle that engineers use to build submarines or missiles. Not because nature copies machines, but because machines mimic the physics of survival that nature has refined. This is particularly evident in species like the sailfish, often clocked as one of the fastest fish in the ocean. It combines lightning-fast acceleration with a collapsible sail dorsal fin, used for maneuvering and intimidation but stowed away mid-hunt to cut through the sea with less drag. In prey-rich zones, the sailfish will dart among panicked baitfish with surgical turns, its long bill slashing through as a hydrodynamic blade. Not brute force, not power, just speed and design. Even the prey themselves reflect the necessity of velocity. Tuna, fast, muscular, and constantly in motion, are among the hardest meals to catch in the sea. This in turn pressures their predators to become even faster, more precise, more evolved. It's not just an arms race of strength. It's a race of engineering, evolutionary prototypes versus natural upgrade cycles. The predators that rule the open ocean today are not just hunters, they are biomechanical success stories. And so the ocean remains a crucible of acceleration, not just because it's vast or empty, but because it demands motion without forgiveness. In a world where there is no place to ambush, no coral wall to wait behind, and no reef ledge to hide beneath, everything happens in the open. A straight line of attack, a blur of pursuit, a kill at full speed. Speed here is not an advantage. It is a requirement, a baseline, a fundamental currency in a biome where hesitation equals hunger and a delay means death. From the sleek torpedoes of the swordfish to the explosive bursts of the mako shark, from the coordinated charges of dolphins to the slicing chaos of sailfish strikes, every design, every twitch of muscle, every flick of a tail is part of this relentless arms race. Born for speed, these animals are not just predators. They are the inevitable products of an ocean that punishes anything slower than excellence. In the blue desert of the open ocean, a shadow flickers below the surface. Not a drift, not a glide, but a jolt. A sudden, purposeful displacement of water, as if something had snapped loose from gravity itself. It vanishes almost as quickly as it appears. But if the camera catches it just right, framed by a curtain of filtered light and the silence of depth, it reveals the unmistakable outline of a predator built for one thing: high-velocity assassination. The shortfin mako shark, Isurus oxyrhynchus, doesn't cruise like other sharks. It launches. It doesn't circle or stalk. It arrives. And when it does, it moves with a speed that ruptures expectation. A living missile tearing through liquid resistance with the purpose of a bullet and the agility of a cat. Unlike the lumbering patrols of tiger sharks or the circling menace of great whites, the mako has no time for theatrics. Its body is designed for one thing: speed. Every muscle fiber, every tendon, every fin placement and skin ridge works in service to that one evolutionary goal. A streamlined, spindle-shaped body tapers into a powerful crescent tail built not for gliding, but for explosive thrust. The dorsal fin is relatively short and swept back, reducing drag while still offering control. Its pectoral fins are narrow and angled, allowing for agile pitch adjustments even during high-speed pursuits. But it's what lies beneath the skin that truly sets the mako apart. Most sharks are ectothermic. Their body temperature depends on the surrounding water, but the shortfin mako is among the rare few that evolved partial endothermy. Through a specialized structure called the rete mirabile, a complex network of capillaries that conserves heat, makos can warm key muscles, their brain and their eyes. This allows for sustained muscle efficiency even in colder waters and gives them a neurological edge when milliseconds count. In practical terms, it means that while their prey begins to fatigue from bursts of speed, the mako accelerates, thinking faster, processing motion faster, and striking before the other animal's nervous system can fully react. Their typical targets are no easy catch. Tuna, mackerel, and swordfish are among the fastest swimmers in the sea, capable of agile dodges and burst sprints. But the mako does not chase endlessly. It selects its moment with the precision of a tactical strike. From below or behind, using a mix of visual cues and electroreception to track the electrical signals of moving muscles, the shark calculates a path. And then, without warning, it erupts. Speeds of 50 miles per hour have been recorded, faster than any other known shark, and enough to tear through a school of tuna like a torpedo through confetti. The strike isn't clumsy. It doesn't rely on brute force alone. The mako's upper and lower jaws are lined with long, slender teeth, slightly curved, needle-sharp, and capable of shearing through dense muscle and bone. Its bite, though not as crushing as the great whites, is optimized for slashing and tearing. One pass can disable or kill. Two can reduce even large prey to ruin. And because its metabolism runs hot and fast, the mako wastes little time. It feeds, it moves, it hunts again. Breaching, although more commonly associated with great whites, is also a weapon in the mako's playbook. High-speed vertical attacks sometimes end with the shark hurtling meters into the air, twisting mid-flight before slapping back into the water. These breaches aren't acrobatics for their own sake. They're the result of chase momentum, high-velocity vertical attacks that carry the shark past its prey and into the air. It's a consequence of hunting at such extreme speeds that even gravity feels like an afterthought. Interestingly, the mako's high-performance physiology comes with unusual trade-offs. It burns energy faster than most sharks. It requires a near-constant intake of calories to maintain its pace. This forces it into a cycle of continuous motion, not just because, like many sharks, it must swim to ventilate its gills, but because its body demands fuel. This need for high-energy prey is why it seeks out fast fish. Slow, soft-bodied creatures aren't worth the effort. The mako's hunting economics are as unforgiving as its speed. In its behavior, the mako breaks several assumptions people often hold about sharks. It is not a mindless glider or a sluggish opportunist. It is alert, reactive, and even unpredictable. Observations from tracking tags reveal that makos can cover hundreds of kilometers in a matter of days, zigzagging between depths and thermal layers, sometimes diving below 500 meters before rising again to strike. This vertical mobility adds a new axis to its hunting strategy, a three-dimensional awareness that allows it to exploit prey movement in open water with tactical precision. Despite their solitary nature, makos exhibit signs of learning and adjustment. In controlled studies and tagging programs, individuals have been shown to alter their hunting routes and depths in response to seasonal prey migrations. Juveniles especially tend to target smaller or schooling fish, honing their strike techniques as they mature. Adults become more refined, favoring single, high-value targets like large tuna or billfish, where a successful strike pays off in a dense, calorically rich meal. Their aggression is also well documented. Among all pelagic sharks, the mako is one of the most likely to approach boats, even ramming or leaping into them on occasion. Not out of recklessness, but because its threshold for fear is simply lower. This is a predator that treats risk as part of the job, and it often survives because it is the faster one to act. In the broader ecological picture, the short-fin mako fills a vital role. It keeps populations of fast-moving pelagic fish in check, balancing ecosystems that would otherwise suffer from unchecked proliferation of smaller, faster schooling species. Without predators like the mako, open-water food chains would clog and collapse under their own weight. By preying on the strong, the swift, and the evasive, the mako maintains a brutal kind of equilibrium. Its presence is a reminder that the ocean rewards not just power, but precision. In a world where most hunters rely on ambush or attrition, the mako is a sprinter, a calculated assassin with a physiology tuned for pursuit. It hunts in plain sight, in open blue voids where there is nowhere to hide, and it still wins. Everything about the mako shark defies standard marine logic. Its speed exceeds expectation. Its heat control challenges classification. Its strategy is more refined than it appears. It's a creature that evolved not by bending to the rules of its environment, but by rewriting them. In the open ocean, where water resists every movement and energy is currency, the mako is a predator that thrives by breaking every rule, except one: be faster than everything else, or die trying. In the warm, translucent waters of the subtropics, where sunlight penetrates deep and shoals of fish shimmer like quicksilver, a formation begins to take shape beneath the surface. Not a random cluster, not a disordered gathering, but a coordinated, deliberate assembly of apex hunters. A dolphin pod, 30 strong, is moving in formation, each individual adjusting its angle and velocity with minute precision. Their silhouettes slide through the water like shadows given form, quickening and weaving in tight spirals. To an untrained eye, it may appear chaotic, but every movement has purpose. Every twist, every roll, every arc in the water is part of a high-speed strategy that turns individual agility into overwhelming group efficiency. Unlike solitary predators that rely on brute force or stealth, dolphins, particularly the common bottlenose, Tursiops truncatus, and spinner dolphins, Stenella longirostris, weaponize collaboration. Their power is not merely in speed, but in synchronization. And in the open ocean, where prey are fast, elusive, and alert, a single dolphin can only do so much. It is the pod that becomes the apex tool, an organic, fast-reacting, multi-agent system designed to trap, corner, and consume. Their target? Sardines, anchovies, mackerel, schooling fish that move like living storms, splitting and reforming in fractions of a second. But speed is not enough to escape dolphins, because dolphins don't just chase, they direct. The first step in the assault is location. Dolphins rely on echolocation not only to detect prey, but to measure their density, spacing, and speed. They emit a rapid series of clicks, pulses that bounce off fish bodies and return in milliseconds. Each dolphin receives a sonic picture of its target, not as a blur, but as a detailed moving image sculpted in sound. Unlike visual hunting, echolocation gives them the advantage of seeing in all directions, even through muddy water or darkness. And while one dolphin scan is impressive, a group scanning together can paint a three-dimensional dynamic map of the prey school, adjusting positioning accordingly. The hunt begins with flanking maneuvers. Dolphins spread out, forming a perimeter around the fish, often in a crescent or circular pattern. The outer edge of the formation is constantly in motion, creating pressure, funneling the fish inward. As the school tightens, dolphins at the rear begin to generate confusion, accelerating in bursts, diving beneath the school, and then lunging upwards, forcing fish to rise toward the surface. If needed, they use tail slaps and bubble streams, disorienting behaviors that further break the cohesion of the school. The fish, which evolved to survive by swimming as a single dense swarm, begin to panic under the precision of this pressure. Soon, the target fish collapse inward, forming a baitball, a last-ditch defense mechanism in which fish group tighter and tighter into a rotating sphere, trying to confuse the predators by moving as a unified whole. But against dolphins, this tactic only seals their fate. A baitball simplifies the target zone. It concentrates the prey. It allows dolphins to rotate through feeding passes like synchronized swimmers, taking turns to dart into the ball, snatch a mouthful, then exit cleanly to reset. The efficiency is mechanical. Each dolphin waits its turn, avoiding chaos or collisions, feeding without destroying the formation, so the rest of the pod can continue to exploit the cluster. What makes this method extraordinary isn't just the coordination, but the speed at which it happens. In these feeding blitzes, dolphins are capable of acceleration and turning speeds that rival the most agile fish. Their flexible vertebral columns, combined with powerful fluke-driven propulsion, allow them to corkscrew, loop, and pivot mid-chase. Unlike sharks or swordfish, who often commit to long arcs or straight-line sprints, dolphins function like underwater fighter jets, able to alter their trajectory in the blink of an eye. A turn radius of less than a body length is not uncommon. This agility is magnified in a pod setting, where multiple dolphins navigate within meters of each other without misstep. Speed is not just for catching prey, but for maintaining control. The faster the dolphins move, the more pressure they apply to the bait ball, but high velocity alone isn't enough. The real skill is in modulated speed, surging, stopping, redirecting, accelerating again, all without telegraphing their next move. And they do so not through verbal commands or pre-planned tactics, but through micro-behaviors and real-time observation. A flick of a pectoral fin, a shift in trajectory, a minor change in rhythm. These are the cues that synchronize the group. Over time, through learning and repetition, a pod becomes more than the sum of its individuals. It becomes a single hunting organism. Unusual strategies also emerge depending on environment and pod composition. In shallow lagoons, dolphins have been observed using the seabed itself as a trap, chasing fish toward the shore, then sliding onto the mud flats to grab them before wriggling back into deeper water. In deeper pelagic zones, they will use air bubbles not just to disorient prey, but to sculpt and compress the bait ball into more manageable density. In some regions, dolphins even work alongside other predators. Temporary alliances form between dolphins, seabirds, and large fish like tuna, all targeting the same prey cloud from different angles. Each predator species brings a different method. The dolphins manipulate, the tuna surge, the birds dive, and the ocean turns into a spiraling vortex of precision feeding. Juvenile dolphins, while often included in these hunts, begin on the periphery. They watch the formations. They mimic the tail slaps. They test their own lunges and feeding dives on the edges of the bait ball. Learning is both passive and participatory. Young dolphins are rarely scolded or corrected, but they are also not fully included in the inner circle until their movements are refined enough not to disrupt the hunt. Over time, this apprenticeship yields adults that understand not just the motion, but the timing of the attack. When to surge, when to peel off, when to reset. The sensory load during these moments is immense. Rapid echolocation, constant visual scanning, spatial awareness of other pod members, fluid awareness of the prey school's trajectory. All of it must be processed in real time. But dolphins are uniquely equipped for this cognitive demand. Their brains, among the largest of any non-human animal, are wired for high-level social interaction and real-time decision-making. Hunting in this context is not instinct alone. It is cognition in motion, a behavior that blends memory, perception, and communication into one seamless execution. The entire event, from initial contact to full consumption, may last less than 10 minutes. But in that time, the sea transforms. What was once a free-moving, self-organized school of fish becomes a compressed, churning mass of panic, and then silence. The water is littered with scales, a few drifting bubbles, and the slow descent of displaced sand. Dolphins regroup briefly before fanning out once more, searching for the next signal, the next flicker of life to target. Pod hunting isn't just a marvel of nature. It is one of the most sophisticated group hunting strategies observed in the animal kingdom, comparable in complexity to wolf-pack dynamics or orca predation, but with the added challenge of operating in a fully three-dimensional space. Every element, from echolocation to muscle control, from social roles to tactical variation, contributes to a predatory strategy that is both fluid and brutally effective. In the hierarchy of ocean hunters, dolphins defy traditional definitions. They don't possess venom. They lack claws or jagged teeth. They do not ambush from darkness or rely on overwhelming size. What they do possess is something far more formidable in the open sea: precision teamwork, unspoken coordination, and a mastery of movement that turns speed into control and control into survival. In the world of torpedo predators, the dolphin stands alone as the architect of aquatic ambush, not with stealth, but with collective momentum, timed perfectly to the rhythm of the hunt. In the temperate layers of the open sea, where light begins to fade into blue haze and the water grows cooler with every descending meter, a lone predator emerges from the dimness like a moving spear. Long, lean, and almost metallic in its sheen, the swordfish travels without fanfare, not stealthy in the traditional sense, but with such silent confidence that the ocean seems to part in its wake. It doesn't stalk from shadow or spring from ambush. It comes forward directly, slicing through the water with a bill longer than its own head and a body engineered to maximize momentum. It does not need to hide. Its speed is its surprise. This is Siphius gladius, the broadbill swordfish, one of the ocean's most underrated hunters and one of the fastest. It has no teeth, no venom, no massive jaw structure. But what it does have is one of the most effective biological weapons in marine evolution: a flattened, double-edged, bone-hard bill that functions as both a hydrodynamic aid and a devastating tool of attack. In motion, the swordfish cuts through the sea with barely any resistance. Every fin is recessed, the skin is slick and scaleless, and the body shape is built to generate as little drag as possible. The dorsal fin folds into a groove, the pectorals press flat. It becomes a living arrow, and when it strikes, it does so with the precision and violence of a torpedo tipped with a blade. But what separates swordfish from other marine sprinters is not just their speed or weaponry, it's their internal physiology. The open ocean, especially in deeper zones, is cold. For most fish, that means slower reflexes, dulled senses, and sluggish muscle performance. Swordfish have circumvented this with a rare adaptation: cranial endothermy. Through a network of heat-exchanging blood vessels near their brain and eyes, swordfish can maintain these critical areas at temperatures significantly warmer than the surrounding water. In effect, they operate with a heated guidance system. Their eyes respond faster, their vision remains sharp even in dim conditions, and their brain processes movement and spatial data with a clarity that most marine creatures can't achieve at those depths. This thermal boost gives them a significant edge in the midwater zone, the twilight layer where many prey species congregate in dense schools during daylight hours. Here, sardines, herring, squid, and mackerel drift in defensive clouds, suspended between the darkness below and the predators above. Swordfish exploit this vertical trap zone with startling efficiency. Rising from deeper waters, they target the edges of schools with sudden explosive bursts. They don't lunge to swallow prey. Instead, they slash. With one or two quick lateral flicks of the head, the swordfish swings its bill into the mass of prey, stunning or killing multiple fish at once. The movement is precise and rapid, a blur to the naked eye. It doesn't matter whether the fish are facing toward the attack or away from it. The strike is too fast, the range too wide. Some victims are impaled. Others are simply struck hard enough to be rendered immobile. The sword's surface is rough, ridged with tiny abrasions that increase its cutting power. Laboratory analysis has shown that the tip of a swordfish bill can withstand incredible stress, and it often shows wear and tear, evidence of frequent violent impacts. In some individuals, the sword has even been observed to regrow slightly after damage, suggesting a biological tolerance for breakage and a design optimized for repeated use. After slashing, the swordfish circles back and begins to consume the immobilized prey. Despite their aggressive attack style, they feed with measured bites. Unlike sharks or other carnivores, swordfish don't tear large chunks or dismember their meals. They tend to swallow prey whole, taking advantage of the moments after the kill while the prey is still drifting. This secondary phase of the hunt is calm, almost surgical, in contrast to the chaos of the initial strike. Observations from submersibles and tracking data reveal that swordfish often hunt alone. There's no pod, no coordinated pack behavior. Their success is rooted in speed, stealth, and ambush executed by individual calculation. Yet despite their solitary nature, they're remarkably adaptive. Some swordfish are known to make vertical migrations of several hundred meters per day, spending the daylight hours in cooler, deeper waters before rising at night to hunt near the surface. This movement matches the behavior of many mesopelagic prey species, and the swordfish follows the vertical shifts with almost clock-like precision. In rare but telling cases, swordfish have even been recorded attacking creatures far larger than themselves. There are documented incidents of swordfish impaling sharks, whales, and even submersible vehicles, not necessarily as a hunting strategy, but possibly as defensive behavior or competitive displays. One recorded swordfish was found with its bill lodged deep into the body of a big-eye thresher shark, a wound that likely proved fatal to both. While these encounters are outliers, they reflect a deeper truth about the animal. It is not passive. It will engage with force when provoked or challenged, and it will use its bill with deadly consequence. Physiologically, the swordfish's power is sustained by a large red muscle mass along its flanks, which provides both stamina and explosive bursts. These muscles are well oxygenated, feeding on the high-protein diet that comes from high-speed predation. The tail, lunate and rigid, drives it forward with minimal side-to-side movement, maximizing thrust while minimizing wasted motion. Combined with a rigid spine and torpedo-like body, this enables acceleration that rivals the fastest sprinters in the sea. While not as nimble as a dolphin or as maneuverable as a reef hunter, the swordfish makes up for it with direct speed and straight-line power, a weapon that does not turn easily, but strikes hard. One of the most fascinating aspects of swordfish hunting is the contrast between its violence and its silence. Attacks are rarely seen, even less often heard. A school of mackerel might scatter for a second, glints of silver flashing in all directions, and then silence again, as if nothing happened. But if a researcher revisits the site moments later, the signs are clear: floating scales, blood trails, and a few stunned fish spiraling downward. The swordfish is already gone, back into the blue, its appetite sated for the moment, its role as a mid-ocean predator once again complete. In an ecosystem driven by bursts of energy and brief windows of opportunity, the swordfish has carved out a niche defined by precision and force. It doesn't need to patrol in numbers or rely on teamwork. It doesn't need to overpower prey with brute strength or ensnare them with traps. It uses temperature to sharpen its mind, a blade to harvest its meals, and velocity to control every encounter. Every part of its anatomy, from the reinforced skull to the high-speed tail propulsion, has been shaped by this specialized strategy. And despite its solitary habits and silent strikes, the swordfish remains one of the most respected and efficient predators in the open sea. Not because it dominates with bulk, but because it has mastered the art of the single decisive moment. A sword drawn only when needed, and always with purpose. Far from shorelines and coral sanctuaries, past the continental shelf where the seafloor plunges into abyss, lies the realm of the open ocean. A habitat so vast and empty, it appears almost featureless. Here the sea stretches without structure, without boundaries, without the landmarks that define life along the coast or among the reefs. There are no hiding places, no ambush points, no surfaces to cling to. Just an endless shifting volume of water, shaped only by currents, light, and pressure. For predators that choose to live and hunt in this environment, every pursuit becomes a test of precision, timing, and endurance, in a space where the only cover is distance and the only advantage is movement. Unlike the coral reef or kelp forest, where stealth and stillness are viable strategies, the pelagic zone demands something different. In this open battlefield, motion is not just a means of travel, it is a language, a defense, a weapon. Prey do not rely on camouflage or concealment, but on speed and cohesion. They move in tightly coordinated groups, shifting direction in perfect synchrony to confuse and evade. Predators, in turn, must learn to strike with split-second accuracy, often closing the gap across tens of meters in a single committed burst. The hunt here is not about deception, it is about velocity. This oceanic stage hosts some of the most specialized chasers on Earth. From the swordfish and mako shark to tuna and sailfish, these animals are built for speed not just in form, but in function. Their lives unfold in 3 dimensions, navigating a vast aquatic void with no terrain to use to their advantage. For them, every successful kill demands rapid calculations. Trajectory, acceleration, turn radius, distance to target, performed instinctively at high velocity. The pursuit is immediate and unforgiving. There are no second chances. Miss the mark, and the opportunity vanishes into the blue. Predators in the pelagic zone face a particular challenge: water itself. It is nearly 800 times denser than air and far more resistant to motion. High-speed movement through water is a constant battle against drag, which increases exponentially the faster an animal moves. This means that any sustained burst must be efficient, well-timed, and purposeful. Wasting energy here is not a minor inconvenience. It is a threat to survival. An unsuccessful strike can drain reserves that may not be replenished until the next kill, which could be hours or even days away. Unlike terrestrial predators that can rest or hide between hunts, ocean chasers must remain in motion, sometimes for their own respiration. Some, like tuna and mako sharks, are obligate ram ventilators, requiring constant forward movement to breathe. For them, the chase is life. There is a parallel here to aerial combat, a comparison that becomes clearer when observing how these predators interact. In dogfights between fighter jets, speed is critical, but so is maneuverability, anticipation, and the ability to lock onto a fast-moving target in 3-dimensional space. The same dynamics play out beneath the surface, where predators must adjust their trajectory in milliseconds, banking through turns and rolling their bodies to align their strike path. They approach from behind, angle themselves below the prey to remain unseen against the dim light filtering from above, and wait for the precise moment when acceleration will lead to interception rather than evasion. It is not a chaotic dash. It is a calculated engagement, one that mimics the physics and tactics of engineered flight, but with the added complexity of resisting drag in a compressive medium. Prey are not passive in this battle. Many pelagic fish have evolved not only fast-twitch muscle fibers for quick escapes, but also social tactics that amplify their defenses. Schooling behavior, often mistaken for simple clustering, is a highly evolved survival strategy. The tight formations of sardines, anchovies, and mackerel confuse predators by presenting a constantly shifting mass of bodies. Sudden directional changes create visual overload, making it harder for a predator to isolate and lock onto a single target. This effect is enhanced by the reflective scales of many baitfish, which scatter light in every direction, creating a kind of strobe effect that further obscures movement. In response, predators have developed equally sophisticated strategies. Some, like sailfish, rely on coordination among a loose group of individuals. They take turns striking into the baitball, reducing competition while maximizing efficiency. Others, like dolphin pods, manipulate prey movement by surrounding and compressing schools from multiple angles, using speed as both a threat and a control mechanism. Solitary hunters like the swordfish adopt a different approach, exploiting vertical ambush by rising rapidly from deeper waters where they are harder to detect, making use of their cranial endothermy to maintain cognitive sharpness during deep dives and rapid ascents. The open ocean also removes any element of territorial advantage. Predators here cannot claim and defend a hunting ground in the way a reef-dwelling moray or a coastal octopus might. Everything is mobile. The predator, the prey, the current, the thermal layers. A patch of water that teems with fish 1 hour may be barren the next. This forces predators to be perpetual scouts, moving across immense distances, reading changes in water temperature, salinity, and current patterns to anticipate where prey might be. In this sense, hunting becomes an act of environmental interpretation, not just brute pursuit. Even sensory perception is tested in this environment. Sound travels faster and farther in water than in air, but so does visual distortion. Light refracts and fades with depth, limiting sight lines and complicating motion detection. Many predators evolve eyes that are both sensitive to dim light and capable of rapid refocusing. Some species, like tuna and swordfish, use specialized retinas and brain cooling systems to improve visual processing during high-speed encounters. Others rely more heavily on the lateral line, a series of mechanoreceptive organs along the flanks that detect vibrations and water displacement. These systems work together to create a composite awareness of motion, allowing the predator to chase not just what it sees, but what it feels. Occasionally, multiple predators from different species converge on the same prey school, creating a multi-level hunting event. Dolphins, sharks, tuna, and seabirds may all participate in what becomes a full-spectrum assault from above, below, and laterally. These events resemble coordinated strikes, though each predator acts according to its own methods and timing. The effect on the prey is overwhelming. Confusion, compression, and collapse into baitballs that further simplify the predator's task. In these moments, the open ocean feels anything but empty. It becomes a war zone of fluid motion, rapid decision-making, and strategic improvisation. What makes these interactions so compelling is their balance of brutal efficiency and elegant mechanics. There is no wasted energy, no flamboyant displays. Every movement is tuned to the environment's demands. It is nature stripped to its essentials, a test of who can accelerate faster, maneuver tighter, strike cleaner, and endure longer. Unlike the brutal collisions of land predators or the deceptive snares of benthic hunters, pelagic predation is an art of constant motion. To live in the open sea is to chase shadows on an invisible stage, where the rules are written in momentum and the cost of hesitation is starvation. In this expanse, there are no boundaries to flee to, no corners to hide in, and no higher ground to retreat toward. Everything happens in the open. The ocean does not offer shelter, only distance. And that distance must be closed. By speed, by strategy, by sheer biological engineering. It is a battlefield not of force alone, but of refinement. The predators that succeed here do so because they have mastered the dynamics of pursuit in a medium that punishes imperfection. In the open ocean, survival is not about who is strongest or most cunning. It is about who can make motion itself a weapon and never stop moving. The difference between life and death in the open sea often boils down to timing measured not in seconds, but in fractions so small they barely register. To the human eye, at least. A sailfish curves its streamlined body and accelerates in a flash, its sails snapping shut as it spears through a panicked school of mackerel. The prey scatter a heartbeat too late, just enough for one to fall within the strike radius of the predator's bill. In that fleeting moment, a neurological calculation has already been made. Not just a decision to act, but a full sensory motor exchange. The detection of motion, the translation into muscular command, and the full body execution of an ambush. All completed before the mackerel's own reflex pathway has even fully registered the incoming threat. This is not a contest of strength, it is a race between nervous systems. In the high-speed world of pelagic predation, the predator's body is a tool, but its brain is the true weapon. Reflexes alone are not enough. A fast body without a fast brain is like a race car driven by a slow pilot. The potential for speed is there, but the decisions arrive too late. To catch agile prey in the open ocean, a predator must not only move quickly but think quickly. The process of predation begins the moment movement is detected. A flicker in the periphery, a change in light patterns, a subtle shift in water pressure. Visual input is collected, interpreted, and acted upon in a blink. And in that blink, one animal dies and another survives. Species like the sailfish, mahi-mahi, and yellowfin tuna are renowned not just for their speed, but for their reactivity. When viewed in ultra-high-speed footage, what seems like a single fluid motion, a strike or a turn, reveals itself as a cascade of micro-adjustments. A sailfish launching toward a prey ball doesn't simply charge in a straight line. Its head tilts slightly to adjust its bill's alignment with the fish. The body flexes incrementally to avoid a collision with another predator. The dorsal fin tucks down to minimize drag, while the pectorals flare out just enough to maintain pitch. These adjustments happen in rapid sequence, each one triggered by a change in visual or proprioceptive data, a kind of biological feedback loop that operates at astonishing speed. The ability to process such information relies on a highly developed nervous system, And in many oceanic predators, neural conduction speed is a critical part of the equation. Myelinated nerve fibers, which are coated in a fatty sheath that increases signal transmission, are common in fast-chasing fish. The thicker the myelin, the faster the signal can travel, reducing the time it takes for a visual cue to become a muscular response. In some of these species, particularly billfish and tunas, the signal from the eye to the spinal cord to the tail can travel fast enough to trigger a body-wide reaction in just a few milliseconds. But there's more than speed at play. The brain must also make correct decisions. In a tightly packed baitball, a predator can't afford to simply strike at random. It must identify the right target, often the one showing signs of fatigue, the one slightly out of alignment, or the one reacting a split second slower than the others. This requires pattern recognition, not just motion detection. Neural centers in the optic tectum and midbrain process streams of visual data, not only analyzing direction and speed, but predicting where the prey will be by the time the predator's body arrives. It is predictive targeting, not unlike a quarterback throwing a pass to where a receiver will be, rather than where they are. This kind of anticipation is the key to successful hunting at high speed. Consider the mahi-mahi, or dolphin fish, a vivid iridescent predator known for its blistering acceleration and erratic angular pursuit paths. When chasing flying fish, the mahi-mahi doesn't follow directly, but tracks the trajectory with precision, predicting the prey's next leap, adjusting mid-chase in a zigzag pattern through the water column. As the flying fish breaks the surface and glides, the mahi-mahi launches upward, timing its own breach to intersect the glide path. This level of coordination requires not just physical speed, but a split-second analysis of trajectory, wind resistance, angle of launch, and surface reflection, all executed subconsciously through deeply tuned neural architecture. Prey too have evolved to operate within this neurological arms race. Many schooling fish like sardines and anchovies exhibit extraordinarily fast startle reflexes. Triggered by a specialized nerve cell system, the mouth nacelles, their bodies can flick away from a stimulus with near instantaneous reaction times. The startle response is so quick that it bypasses the higher brain centers entirely, relying on a direct synaptic connection between the sensory organ and the motor neuron controlling the tail. It's a reflex designed not for strategy, but for raw escape. But while this helps the group, it lacks the nuance of the predator's calculated strikes. Interestingly, speed without control can be counterproductive. Some of the fastest fish in the sea, like wahoo, possess remarkable acceleration, but are less successful in hunts requiring fine maneuvering or precise targeting. Others, like sailfish, combine acceleration with a brain that can manage those speeds with tight, accurate timing. Studies have shown that in predator-prey chases, the winner is often the animal that can adapt its path mid-pursuit, not just the one that begins faster. This neural flexibility, the ability to process updated information during a chase and adjust accordingly, becomes more important than sheer top speed. One often overlooked factor in this equation is the environment itself. In clear, sunlit waters, visual processing dominates. But in deeper, dimmer zones, visual input diminishes, and predators must rely on lateral line sensing and electrosensory feedback. Species like the blue marlin and swordfish often strike in low-light environments, where their heated brains and eyes maintain faster image processing even as the water temperature drops. This allows them to react more quickly to subtle changes in prey behavior, even at depths where other predators struggle to function effectively. Slow-motion analysis of predatory strikes reveals just how nuanced these interactions are. A sailfish approaching a baitball may feint a strike, a partial movement that triggers premature reactions from the fish school, then adjust and strike in the resulting confusion. These false moves suggest cognitive strategies rooted not only in timing, but in manipulation of prey behavior. It is a dance of microsecond decisions, where the predator not only moves quickly, but manipulates the response window of the prey. In this way, the predator's brain becomes not just a processor of data, but an active participant in shaping the prey's reaction. What emerges from all this is a deeper understanding of how evolution shapes not just muscles and fins, but minds. In the realm of speed-based hunting, intelligence is not always about learning or memory. It is about timing, perception, and the ability to respond to environmental input with lethal efficiency. The ocean rewards those who can process the flood of sensory data and translate it into motion with zero delay. In the vast and unforgiving expanse of the open sea, no structure or shelter offers a second chance. Every chase is a single high-stakes equation of motion, prediction, and neurological firepower. Those who survive, and those who dominate, do so not because they are the strongest or most aggressive, but because their brains are calibrated to extract milliseconds of opportunity from the fluid chaos of the hunt. And in those milliseconds, entire lives begin and end. The midday sun spills through the water column in shafts of light, casting crisp silhouettes of drifting plankton and suspended air bubbles. It is the kind of clarity that turns tropical shallows into underwater theaters, every movement visible, every ripple amplified. In this calm, the prey drift with an illusion of safety, lulled by the seeming openness of their surroundings. But in these clear waters, death comes not from above or below, but from within the very frame of their vision. It comes fast, straight, and with no warning. It comes in the form of a living blade, a flash of silver muscle propelled like a thrown spear. The strike lasts no longer than a blink. The water convulses, and where there was once a fish, there is only a puff of scales spiraling toward the surface. This is the domain of the ambush sprinter, predators that do not chase, do not strategize, and do not wait. They strike from rest. They strike with explosive violence, and then they vanish into stillness again. At the forefront of these killers are the barracudas and the needlefish, built not for endurance or teamwork, but for instantaneous, devastating acceleration. The great barracuda, Spherina barracuda, is often mistaken for a simple opportunist. Its elongated, torpedo-shaped body and slack-jawed grin give it a menacing, almost reptilian appearance. Yet beneath that still exterior lies a musculature engineered for sudden violence. Unlike tunas or sailfish that rely on sustained speed, the barracuda operates on the principle of maximum output in minimum time. Resting quietly among seagrass or hovering near a reef edge, it waits for the moment a fish enters its kill zone, usually a lateral arc extending only a few meters ahead. Within this limited range, it is almost unbeatable. The moment it launches, the entire posterior half of its body whips into a C shape, coiled and ready, before snapping straight with brutal torque. The tail, wide, deeply forked and stiff, generates a single explosive push, propelling the barracuda forward at speeds estimated up to 43 kilometers per hour in a burst covering its own body length in less than a second. The jaws open slightly mid-strike, not to grab but to reduce water resistance, before clamping down with rows of long, fang-like teeth. These teeth don't crush, they slice. Arranged in opposing pairs, some are sharp enough to shear through bone. The result is often a clean, almost surgical amputation of the prey's back half, leaving the head and gills drifting lifelessly behind. A macabre signature of a predator that wastes no energy where none is needed. Unlike sharks or group hunters, barracudas don't rely on chase endurance. Their energy is conserved until the strike, and their kills are nearly always one-motion affairs. They do not circle or finish off wounded prey. If a fish escapes the first strike, it is rarely pursued, not because the barracuda cannot follow, but because its efficiency is predicated on certainty. That precision makes them extraordinarily selective hunters. They'll often wait minutes, even hours, for the right-sized fish to stray close enough. Not too small, not too alert, not too fast. The success rate of their strikes is high because they only strike when the odds favor them completely. In crystal-clear lagoons and sunlit reefs, this tactic can be seen in full cinematic clarity. A glassfish or juvenile jack darts across the frame, its scales catching the sunlight. Then the camera shudders with impact. A blur of silver as the barracuda flashes through, trailing a brief distortion of current and micro-bubbles. By the time the image steadies, the prey is gone or broken. There is no drawn-out chase, no dramatic build-up, just clean, decisive termination. This immediacy, the sudden transition from stillness to violence, is what makes ambush sprinters such terrifyingly effective predators in their niche. Needlefish, from the family Belonidae, are another example of evolutionary minimalism turned deadly. Sleek, slender, and armed with elongated beak-like jaws lined with razor-sharp teeth, they cut through water like flying daggers. Unlike barracudas, which are ambush predators in tight reef zones, needlefish favor open shallows and surface waters, particularly in calm conditions where light creates a mirror-like film above. From this angle, their prey often doesn't see the strike coming. The needlefish doesn't rise from the depths, but streaks just beneath the surface at blinding speed, snatching small fish from below with an upward flick. Their streamlined body minimizes turbulence, and their dorsal and anal fins, located near the tail, provide rapid stability during high-speed surges. While not as muscular as barracudas, Needlefish rely on a combination of speed and trajectory precision. Their attacks often occur in mid-jump, with many species known to breach the surface entirely during pursuit. Some even glide for several meters before plunging back into the water. This behavior has been well documented, and in rare cases has led to accidental injuries in humans, as needlefish have been known to spear fishermen or swimmers when disoriented by artificial lights at night. The most striking aspect of both species, barracuda and needlefish alike, is how little planning seems to precede the kill. These predators do not coordinate, strategize, or manipulate prey behavior. Their success lies not in teamwork or brain power, but in a brutal calculus of force, speed, and timing. They are instinctive strikers, governed by fine-tuned sensory triggers, a flick of movement, a flash of light, a minor shift in water vibration. That is all it takes to convert a waiting predator into a killing projectile. Behind this simplicity, however, lies a complex sensory system. The barracuda's lateral line, a series of mechanosensory cells running along its flanks, allows it to detect tiny changes in pressure waves created by swimming fish. Its large eyes, forward-facing and highly sensitive to contrast, are ideal for low-light ambush or backlit silhouette detection. Needlefish, with their upward-facing gaze, can spot movement against the reflective ceiling of the water's surface, allowing them to lock onto prey even before the victim becomes fully visible. Neither relies on sound or scent to the degree a shark might. For them, vision and water displacement are the only cues that matter, and they react to those cues with violent efficiency. There is a crude elegance to this hunting style. It doesn't adapt well to uncertainty or distraction. Barracudas, for instance, can be surprisingly inert in murky or crowded environments, where their advantage is dulled. Needlefish struggle in turbulence or low visibility. They are specialists in optimal conditions, light, space, and clean lines of attack. But within those bounds, few predators execute a more immediate, lethal strike. Viewers often look for drama in animal hunts. The drawn-out tension of stalking, the near misses, the chase resolved at the last moment. But blitz predators offer something else: the raw execution of natural engineering. They are less like actors and more like triggers, quiet until they fire. And when they do, they remind us that not all success in the ocean requires intelligence, cooperation, or complexity. Sometimes evolution builds a perfect killer by stripping away everything else, leaving only speed, timing, and the will to strike first. In the clear shallows and reef edges of tropical seas, where light plays tricks and silence rules, the blitzmasters wait. They don't call attention to themselves. They don't need to. Their dominance comes not from control of territory or intimidation, but from the fact that when they move, it is already over. In the open blue off coastal drop-offs and continental shelves, sunlight still penetrates deep enough to ignite the water in luminous streaks, casting long shafts of brightness into an otherwise featureless expanse. Below, the ocean appears empty, silent, suspended, impossibly vast. Then something shifts. A tremble in the currents, a flicker of silver in the deep. One fish darts, then a dozen, then thousands. Within seconds, a tightly packed cluster of sardines swirls into a defensive sphere, a shimmering vortex of scales and panic. The baitball has formed, and with it the countdown begins. What happens next is not a hunt in the traditional sense, but a collision of strategies, speeds, and predatory styles, erupting into one of the ocean's most frenzied spectacles. The baitball is both shield and sentence. By clustering into a pulsating, ever-shifting orb, sardines reduce the chances of any single individual being targeted. Confusion is their only hope, but in the open sea, confusion draws attention, and that attention comes fast. From below, dolphins arrive first. Coordinated, methodical, they flank the sphere, working in precise arcs. This is not a chaotic pursuit for them. It is practiced orchestration. They charge in teams, cutting sideways across the outer edge of the ball to compress it, driving it closer to the surface. Using echolocation clicks, they map the shape and density of the swarm in real time, communicating silently through micro-movements and hydrodynamic cues. Their goal is not immediate consumption, it is containment. Drive the sardines upward, force them into shallower waters, limit their escape routes. Herding behavior at this scale is rare among marine predators, and dolphins excel in its execution, treating the prey mass like livestock corralled against invisible fences. Above, seabirds have already joined the chaos. Gannets and shearwaters wheel overhead, drawn by the flash of silver bodies below. With wings tucked and eyes locked, They plummet from the sky in near vertical dives, slicing through the surface like arrows. Beneath the waterline, they swim with surprising agility, nipping at the edges of the baitball before shooting upward again for air. Their attacks add a vertical pressure, pinning the sardines between danger from above and calculated harassment from below. Enter the tuna. With streamlined bodies and muscles built for endurance and burst, yellowfin and skipjack join the frenzy with brutal efficiency. Their role is not herding, it is disruption. The tuna don't circle, they crash. At full speed, they slice into the baitball with jaws open, scattering fish in all directions. Unlike dolphins, which rely on precision, tuna rely on raw force. Their attacks tear holes in the defensive sphere, temporarily unraveling the school and creating panic, a chaos they exploit with wide, sweeping turns and high-speed loops. Then come the sailfish. Sleek, fast, and absurdly agile, they drift on the periphery, watching the mess unfold. Their approach is almost surgical. When the baitball tightens again, drawn by the surrounding threat, sailfish dart inward with split-second timing, their long bills slashing sideways in quick bursts. The bill is not used to stab, but to stun, breaking the rhythm of one or more sardines with a flick, then circling back to swallow the incapacitated stragglers. Their dorsal sails, when raised, are used to startle or corral, briefly enlarging their apparent size. But when in motion, the sail folds down tight, allowing the fish to accelerate without drag. Few predators in the sea can match their control. The sailfish is a surgeon among brawlers. Sharks, typically slower than their agile counterparts, are the last to arrive. Yet their presence introduces a new dynamic, one of authority rather than finesse. Silky sharks and dusky sharks drift through the feeding cloud with deliberate movement. They do not sprint or dive. Instead, they charge directly through the baitball's core, jaws half open, consuming indiscriminately. The other predators shift slightly at their arrival, not out of fear, but out of wariness. In this high-speed arena, even an accidental collision can result in injury, and the shark's bulk is respected. Their strategy, while less elegant, is effective. They clean up wounded fish, panicked stragglers, confused groups broken off from the main cluster. All become easy targets for a predator that doesn't waste energy chasing, but simply moves through the chaos like a wrecking ball. From a distance, the scene is hypnotic. The baitball spins and flexes like a living organism, its shape changing every few seconds. Spherical, oblong, torn, repaired, responding to pressure from all angles. Each predator, moving according to its own design, contributes to the structure's destruction. The dolphins manage the edges. The birds dive from the top. The tuna cleave through horizontally. The sailfish cut with precision. The sharks scatter and sweep. In this compressed zone of water, measured in meters rather than miles, species that would otherwise compete, or even avoid each other, interact in overlapping roles, driven by one shared objective: exploit the moment before the baitball collapses. Inside the baitball, the environment is one of pure sensory overload. Sardines move not as individuals, but as cells in a single body. They respond to the movement of their neighbors rather than direct observation of predators. This reactionary system creates mesmerizing patterns, waves, spirals, pulses of movement, but it also makes the group vulnerable to manipulation. A sudden strike from a sailfish, for example, sends a ripple through the ball that can expose weaknesses. A vertical breach from a dolphin may force a segment of the school downward into the path of incoming tuna. These manipulations are not coordinated by the predators, but the result of layered behavior, where each species applies pressure in different ways, and chaos becomes the weapon. The sheer energy output of these events is enormous. For predators like tuna and dolphins, participation requires immense bursts of speed, precise turns, and repeated accelerations. Their muscles burn through oxygen rapidly, forcing brief pauses between feeding runs. During these pauses, they circle the periphery, catching their breath, repositioning for the next charge. The baitball never rests. Even a second of stillness could allow the school to scatter and escape. The game is about compression and attrition, gradually breaking down the defenses until the ball collapses into a cloud of drifting bodies. As the attack wears on, the baitball shrinks. The fish remaining are often the most disoriented or fatigued. Gaps form more easily, and attacks penetrate deeper. Eventually, the structure can no longer maintain itself. Some sardines dart for the surface, where they become instant targets for birds. Others dive downward, only to run into sharks or circling tuna. There is no direction that offers safety. What began as a tactic of survival, group defense through unity, becomes a trap. Strength in numbers has an expiration point, and when that point is reached, the feeding tornado ends as suddenly as it began. What remains is a sea of floating scales, faint trails of blood, and predators dispersing in all directions. No one species dominates the event. There is no single victor. Instead, it is a feeding free-for-all governed by timing, technique, and the ability to extract as much as possible from the storm before the energy dissipates. And in that storm, speed is not just a tool, it is the currency of survival. This is where speed meets chaos, not in a straight chase or a one-on-one strike, but in the layered aggression of multiple predators converging on a shared target, each using speed in its own way, each turning the confusion of the moment into opportunity. In the feeding tornado, the ocean reveals a different kind of hunt, one without order, without pause, and without forgiveness. Just motion, instinct, and the soundless violence of the sea. The ocean is not a forgiving place for mistakes. In a world where predators live by velocity and strike in fractions of a second, success is never guaranteed, and failure carries a cost. Out here, in the endless mid-water realms where every burst of speed burns precious energy and every movement must be calculated against fluid resistance, the risk of missing a target is more than just hunger. It is depletion, it is exposure, and in some cases, it is death. High-speed predators are often celebrated for their spectacular kills. The soaring leaps of sailfish, the violent lunges of makos, the precision slashes of swordfish. But rarely do we focus on what happens when these attacks don't connect. The sea, when watched without a romantic lens, reveals countless moments of missed opportunity. The strike too late, the turn too wide, the prey that dodged in just the right instant. These failures are common, and they are costly. A mako shark, after identifying a lone skipjack tuna on the outer edge of a school, coils its powerful tail and surges forward with explosive force. Its streamlined form cuts through the water like a blade, reaching speeds that few fish can match. The tuna, sensing the shift in pressure, accelerates a split second before contact. The shark's jaws close on empty water. The water pressure from the failed strike distorts its path, forcing it to over-rotate, to correct mid-turn. The mako veers off, its momentum spent. From above, it looks like a clean miss. But within the shark, that moment is a drain of vital reserves. Each failed attack burns oxygen. Fast-twitch muscle fibers in pelagic hunters are metabolically demanding. During a high-speed chase, these muscles draw from both stored oxygen and anaerobic energy systems that produce lactic acid as a byproduct. When the strike fails and the predator does not feed, it cannot recover those stores. Instead, the animal must keep swimming, must keep ventilating, and must begin the slow process of flushing that fatigue from its system, all while still vulnerable, still hungry, and now marginally weaker. The same risk applies to the swordfish. Though its bill allows it to strike with reach and force, accuracy is everything. A misaligned slash through a baitball not only yields no food, but can leave the predator temporarily disoriented. In some documented cases, swordfish have been observed sustaining damage to their own bills after striking dense schools or colliding with larger, harder prey. These breaks are not always fatal, but they can reduce feeding success for months, forcing the animal to shift its hunting habits or risk starvation. In an animal so finely tuned for a single method of killing, one miscalculation can compromise its primary advantage. Even group hunters like dolphins are not immune to the risks of failure. During coordinated hunts, a mistimed surge by one member of the pod can disrupt the baitball, sending it scattering before the kill phase begins. Though dolphins possess the social flexibility to regroup and try again, each failed attempt means further exertion. More deep dives, more sonar pings, more sprints through three-dimensional space. While mammals have the benefit of breath control and a more varied energy metabolism than fish, they too must manage their cost-benefit ratios carefully. Wasting time and effort on evasive prey in nutrient-poor zones can mean long, costly relocations in search of new targets. Tuna, built for endurance and speed, face a different kind of penalty. Their hunting style often involves extended chases, punctuated by bursts of intense acceleration. When they fail to close the gap or catch prey during these bursts, they must re-enter cruising mode, burning fuel without the payoff. Their metabolic rate is among the highest in the fish world, and their ability to thermoregulate grants them an advantage in varying temperatures. but even they can overexert. In tropical regions where dissolved oxygen levels are lower, tuna must balance the need to sprint with the risk of running their systems into deficit. They do not have the luxury of rest stops. They must move constantly to breathe, and each miss carries a physiological toll. There is also the matter of exposure. A predator that has just sprinted at full speed is momentarily compromised, not just physically, but strategically. In the seconds following a failed attack, its position is revealed to everything in the vicinity. Other predators may see an opening. Prey schools may reorganize. Opportunistic competitors may swoop in to steal the kill. In the case of dolphins or sailfish hunting near sharks, a miss may invite interference. The sharks, having detected the chemical cues of prey distress or the vibrations of predatory motion, move in to capitalize, not by making their own kills, but by claiming the prize once others have done the hard work. A missed strike leaves the original hunter with nothing and gives the scavenger everything. In some cases, the penalty is injury. Barracudas, needlefish, and other high-velocity sprinters rely on clean, short-distance strikes. When they misfire, for example, when a prey fish veers unexpectedly and the predator strikes coral, rock, or even another animal, the resulting damage can be severe. Their jaws and faces are delicate at high impact. Some needlefish have been observed with broken beaks, skewed jaws, or embedded debris, often leading to starvation. They are missiles with no guidance system, and once the trigger is pulled, there is no turning back. Precision is survival. Imperfection is death by delay. Even the sensory systems of predators are taxed by repeated failures. High-speed chases require rapid visual processing, fast neurological computation, and constant muscular correction. These systems are not limitless. After multiple unsuccessful chases, a predator's reaction times may degrade slightly, its decision-making less sharp. Fatigue builds subtly but relentlessly. A tired predator doesn't simply slow down, it misjudges. And in this world, misjudgment is often terminal. Evolution has shaped these predators to be efficient, but not invincible. They are built for performance, not for forgiveness. The sailfish cannot absorb 20 failed strikes and still swim at full tilt. The mako cannot miss 5 times in a day and expect to hunt again without consequence. Each sprint is a bet, a wager of energy against potential gain. And like all bets, there is risk. Most predators must eat a certain amount each day to maintain muscle function and body temperature. A streak of failures can mean that the margin between hunger and collapse grows razor thin. The baitfish, meanwhile, live on the inverse side of this gamble. For them, each dodge, each last-second pivot, each survival by inches is a win. They expend less energy in evasion than predators do in pursuit, making them well-suited to the war of attrition. This is why prey can survive longer periods without being caught, and why predators must be precise. The cost of missing stacks up fast. There are no energy refunds in the ocean, only consequences. In this fluid arena of speed-based warfare, the margin for error is unforgiving. High-speed hunters are not only designed to kill, they are also built with the silent knowledge that every miss is an erosion of power. The ocean doesn't reward effort, it rewards success. The torpedo hunters of the sea live on that edge, where a fraction of a second decides not just whether a meal is secured, but whether the hunter will have the strength to try again tomorrow. In the high-pressure theater of the open sea, every predator moves under a silent law. There are no second chances, and there is no room for inefficiency. The ocean does not allow for comfort or excess. It refines, it pares down. It selects for those who can accelerate fastest, strike cleanest, and recover quickest. Among the elite of marine hunters, a handful of species have emerged as the ocean's apex racers, not in brute force or size, but in speed, precision, and execution. These are the torpedoes of the sea. But when the stakes are this high and the competition this fast, only one can truly dominate. In this final reckoning, we pit predator against predator. The short-fin mako shark, the broad-bill swordfish, the common bottlenose dolphin, the sailfish, and the great barracuda. Each engineered by nature for high-speed warfare. Each a specialist, each with strengths and limits. The mako shark is, at first glance, a paradox, a heavy-bodied animal that moves like a projectile. Its acceleration is extraordinary, powered by densely packed red muscle and a crescent-shaped tail designed for forward thrust. In short bursts, it can reach recorded speeds of over 70 kilometers per hour, placing it at the top of the marine speed charts. But what makes the mako more than just fast is its control. It possesses partial endothermy, allowing it to warm its brain and muscles, which boosts neural reaction time and power output. It doesn't just move quickly, it processes and adjusts in real time at high velocity. Yet the mako is built for a specific kind of hunting: sudden, violent engagements, often one-on-one. Its stamina is not built for extended multi-angle ambushes, and it lacks the maneuverability to turn inside tightly packed prey schools. It excels in open water sprints, not intricate baitball dances. The swordfish, equally fast in straight lines, plays a different game. Its long, blade-like bill reduces drag and helps slice through schools of fish with powerful lateral strikes. With a highly vascularized system behind its eyes and brain, the swordfish can function at high efficiency in colder, deeper waters, maintaining quick reaction times where others would falter. It is one of the few predators that reliably hunts in both twilight zones and surface waters, using vertical movement as part of its strategy. Yet the swordfish lacks the turning agility of smaller-bodied predators, and while its strikes are lethal, they are based more on sweeping motion and contact zones than precision targeting. It's a powerful, solitary lancer, but one that relies on calculated energy conservation rather than sustained engagement. In contrast, the bottlenose dolphin introduces a level of cognition and coordination that changes the entire equation. Physically, a dolphin's top speed is lower, usually peaking around 35 to 40 kilometers per hour, but this is misleading. Dolphins hunt in pods, leveraging their speed as a unit, synchronizing movements, surrounding prey, and using their acute echolocation to anticipate and react to movement in a way that almost no other marine predator can match. What dolphins lose in raw velocity, they compensate for with maneuverability, stamina, and strategy. They can herd, pressure, and trap. They can make tight, repeated turns without losing momentum. They can adapt their tactics on the fly. And they don't fatigue easily, thanks to their mammalian metabolism and high oxygen reserves. But they are generalists, effective across many scenarios, but not always the most lethal in a one-on-one burst scenario. Then there is the sailfish, the sleek, sail-backed assassin of the tropics. While top speed estimates vary widely, it has been recorded accelerating at phenomenal rates over short distances. Its real advantage lies in maneuverability and accuracy. The sailfish can slash into baitballs with its long bill, stunning fish in rapid, successive bursts. Its fin, raised during hunting and lowered during pursuit, allows it to manipulate hydrodynamic pressure and direction mid-run. It is fast, yes, but also subtle, controlled, and reactive. Sailfish can turn tighter than larger fish, correct course mid-strike, and exit the attack lane before colliding with other predators. Among the apex racers, it is perhaps the most efficient at maximizing strikes per energy unit spent. Still, sailfish are specialized for small, agile prey in tight clusters. They shine in baitball chaos, not in long-distance pursuit or brute force encounters. And finally, the great barracuda, a blunt instrument in a field of scalpels. The barracuda is not elegant, not strategic, not enduring, but it is brutal. From a stationary position, it can accelerate faster than almost any fish of its size, reaching lethal speeds within a body length. Its attack is simple: wait, strike, and retreat. With long, needle-sharp teeth and a powerful jaw, it doesn't chase or corral. It ambushes, and when it connects, the damage is catastrophic. However, its narrow strike zone and poor stamina make it unreliable over time. It is a sprinter with no second wind, dangerous only within a few explosive seconds. To compare these animals is not to crown the strongest or the smartest, but to weigh attributes in context. For raw acceleration and top-end speed, the mako dominates. For deep water, high-efficiency hunting with thermal control, the swordfish stands unrivaled. For coordinated ambush, long-term pursuit, and complex maneuvering, the dolphin takes the prize. For precision strikes within chaotic baitball formations, the sailfish is unmatched. And for sheer simplicity and killing power within short-range, high-speed ambush, the barracuda has few equals. But if we must choose one, not just as the fastest, but as the most well-rounded, most adaptable, and most consistently successful in diverse open water conditions, the title bends toward the sailfish. Not because it is the fastest in a straight line, but because it converts speed into success with relentless precision. It wastes almost nothing. Its movements are purposeful. It can adjust its angle in mid-strike, use its sail to manipulate prey flow, and dispatch multiple fish with a single pass. It thrives in chaos but never loses control. Its efficiency is unmatched. Its success rate among the highest of any pelagic hunter. In the final moments of this underwater showdown, we zoom out, a montage of the ocean's most lethal hunters in motion. The mako explodes upward from the depths, chasing tuna in a straight, brutal charge. The swordfish rises from cold waters, slicing sideways through a school of mackerel with clinical force. Dolphins weave through a swirling ball of sardines, coordinating bursts of speed with exact timing. Sailfish loop in and out of the melee, slashing and resetting with perfect control. A barracuda flicks its tail once and turns a reef passage into a killing corridor. Each of them is magnificent. Each of them has carved out a niche in this brutal, endless race. But if the ocean is a racetrack where survival is the finish line, then it's not just about who is fastest. It's about who makes speed work, every time, with minimal waste and maximum impact. In that race, the sailfish, with its balance of precision, speed, and control, wins not just in motion, but in mastery. It is not the flashiest, not the largest, not the most intelligent, but it is undeniably the most refined racer in the ocean's deadly arms race.